Greetings. I am Hasti from the School of Mechanical Engineering at Purdue University. I will present machine learning models for solar energy forecasting from photovoltaics for given weather parameters in this talk. I sincerely acknowledge Dr. Billy Wu, Professor Kui Jiao, and Professor Jin Zhuan for giving me this opportunity to present this work at the Second International Conference on Energy and AI. I follow a standard outline for my today's talk. I start with a brief introduction, then talk about what motivated to conduct this study and what is the objective of present study, then go over briefly different machine learning models employed for solar energy forecasting, then discuss their results, and finally conclude the presentation with a summary. As you all know, intensified research is going on around the globe to increase the renewable energy sources like solar and wind to reduce the emissions and achieve the Paris Agreement targets, and also to address the depleting fossil fuels resources and meet the increasing energy demand with population. The chart on this slide is taken from the International Energy Agency's recent report, Snapshot of Global PV Markets 2021. As you see in this chart, the total cumulative installed capacity reached approximately 760 gigawatts globally in 2020. In spite of several challenges with COVID-19 pandemic last year, PV market grew significantly with worldwide installation of 139.4 gigawatts of photovoltaic systems in 2020. This informs us that the PV contribution to energy mix is also progressing and help achieve decarbonization goals. In this context, we want to understand how to efficiently operate grid with energy mix. As we all know, the solar and wind are intermittent renewable sources and depends on weather conditions. The penetration of these intermittent renewables causing the fluctuations in the power generation from the fossil fuel-based power plants like coal and natural gas plants. As you see in this chart, by closely looking at the 2 weeks data from 19th Jan to 6th February in 2020, how are these external load fluctuations are affecting the operations of the fossil fuel power plants and communities for electricity? A few plants are closed in the recent past due to financial losses and few more on the verge of shutting down. This is seriously affecting the power supply in those communities. In this digital era, we cannot even imagine our life without electricity. Communities and power plant management are looking for an urgent solution to minimize these financial losses and enable the efficient and reliable operation of grid with energy mix of renewables and non-renewables. So, to minimize losses and enable better integration of renewables and non-renewables in the energy mix, an accurate method of forecasting solar energy is required to make informed decisions about the amount of solar energy available for smart management of utilities and grid operations. In my research group, we are working on artificial intelligence enabled modeling and developing digital tools for smart grid applications to estimate the cost of operations and optimization to enable the efficient and reliable operation of grid with energy mix by controlling the financial losses, fuel consumption, and emissions. Artificial intelligence-based forecasting model should take into account all important weather parameters like temperature, relative humidity, precipitation, solar irradiance, cloud cover, wind speed and direction, etc. And this model has to be well integrated with the smart grid to make well-informed decisions for smooth operations to provide uninterrupted power to the communities. The specific objective is to develop a reliable forecasting model for solar energy from a photovoltaic cell for given weather parameters. The uniqueness of this study is the model with all significant weather parameters included. My work is focused on developing a machine learning framework for short-term and long-term forecasting of solar power for given these important weather parameters. I will be discussing very preliminary results today with few basic machine learning models. This is an ongoing work. I have considered support vector machine model, extreme gradient boosting machine learning model, CAD-boost machine learning model, artificial neural networks model, and ensemble machine learning model in this study. The ensemble model is created by using the linear regression of the values predicted by the ANN, CAD-boost, and XGBoost. Considering the time limit, I am skipping the specific details for each of these models in this presentation. The weather data is collected from the National Solar Radiation Database, National Renewable Energy Laboratory from February 2017 to December 2019. The collected weather parameters are temperature, wind speed, precipitable water, relative humidity, direct normal irradiance, diffuse horizontal irradiance, global horizontal irradiance, clear sky diffuse horizontal irradiance, clear sky direct normal irradiance, clear sky global horizontal irradiance. The UMass Amherst Computer Science Solar Energy Production data from the University of Massachusetts Amherst Energy Dashboard is utilized for the photovoltaic solar power output. This is the power produced by the PV cells placed on the roof of UMass Amherst Computer Science building, as shown in this figure. The power output is collected for the period February 2017 to December 2019, and it is plotted here. I have used 80% of the data for training and remaining 20% for testing the model. The list of hyperparameters for respective machine learning models are shown on the slide. For CAD-boost and the XGBoost, these parameters are n estimators, learning rate, and the depth. For support vector machine model, the hyperparameters are kernel type, gamma, epsilon, and regularization parameter C. And for artificial neural networks model, these parameters are number of hidden layers, number of neurons per layer, optimizer, learning rate, and dropout rate for regularization. The ensemble model uses the hyperparameters optimized for CAD-boost, XGBoost, and ANN model. The values for these hyperparameters are determined using the manual search method in this preliminary study. The performance in terms of root mean square error and R-square value is compared for the 5 machine learning models. The XGBoost model has the lowest root mean square value while the artificial neural network model has the best fit weight for the data with highest R-square value. These are preliminary results, and I exercise caution while making comparisons because these models need further testing and optimization. I am implementing the grid search method for that purpose. The correlation between the predicted and measured values for the photovoltaic cell solar power output is shown for ensemble model, ANN model, CAD boost, and XG boost models. You see a reasonable fit with data centered around 45 degrees slope line. Relatively speaking, the ANN model has shown the best fit among the tested models with the highest R-square value. As I mentioned before, I'm refining these models using the grid search method for hyperparameters, and I'm continuing work with further refinements to these models. That's all I have for today's talk. So far, I have discussed the penetration of the photovoltaics for solar energy generation and its dependency on the weather parameters. A reliable forecast model is important for efficient and reliable operation of the electrical grid with energy mix to enable the continuous availability of electricity. In this study, I have evaluated support vector machine model, XGBoost, CADBoost, ANN, and ensemble machine learning models for photovoltaic cell solar power output prediction. The ANN model has shown the best fit with the highest R-square value. The forecast models in this study are developed with comprehensive list of all important weather parameters for the first time with a goal for reliable forecast model for practical applications. The next steps in this study are, I have used the manual search method in the preliminary study. These models will be further refined using the grid search method. I also plan to include the long, short-term memory networks and extreme learning machine models in the list. I will continue efforts to refine and identify the methodology for short-term and long-term forecasting for solar power output. Now I conclude my presentation. Thank you all for listening to this talk.